When completing his equations of motion, Isaac Newton took notice of a curious thing. They were time-symmetric. The equations do not differentiate between time that is passing forward and time that is passing backward. We always perceive time as moving forward, so for the equations of motion not to hold a bias in this regard seems odd. On its own, the question of why we only experience time moving forward does not seem like a necessary question for us to ask. After all, we can't even really imagine time working in any other way. And when we do try, it's not long before we run into paradoxes that make the idea seem unreasonable. But the fact that the equations do not even hint at this asymmetry combines with this question into what physicists and philosophers refer to as the arrow of time, which is a subject that investigates the relationship between the equations of motion and our ever-present observations of time. Equivalent time theory views this question as somewhat of a category error. Time in the equations, which I will refer to as tau, is not time in the fundamental sense. It is a clock. Furthermore, negative tau does in fact exist and is a property of antimatter. The idea that antimatter has negative tau is referred to as the Feynman-Stuckelberg interpretation. However, it is a mistake to view this as a mere interpretation, as the Planck relation shows us the consequences of the negative energy solutions found with the Dirac equation. Negative energy requires negative frequency, which requires negative tau. So the fact that antimatter has negative tau is not an interpretation, it is a mathematical statement. What is now required is to determine what negative tau represents, not dismiss the existence of negative tau as mere mathematics. The immediate implication is that tau and time cannot be equivalent in the fundamental sense. If they were, and time was accurately represented by the Minkowski metric, we would expect antimatter to travel backwards in time, but we do not observe this. Instead, we observe antimatter traveling forward in time, moving in the same way as matter, while obeying CPT symmetry. When a particle's tau sign flips, charge and parity flip also. Since the rules that govern tau are very similar to the rules that govern the x, y, and z axes, it is reasonable to assume that tau is actually a fourth spatial dimension, invisible at the classical scale, and its coordinate value is best represented as an angle. As the equations of motion are tau symmetric, particles with negative tau should move in exactly the same manner as particles with positive tau, and since tau represents a reversal of an aspect of the physical structure of the particle, we would expect to see a reversal of any symmetries associated with that internal structure. As such, our observations of antimatter constitute the first proof that the central claim of ETT is correct. CPT symmetry is naturally explained by the fact that tau is a physical characteristic, and since it has a symmetric relationship with the passage of time, we have confused the motion of this clock with time itself. Time symmetry, ironically, becomes the solution to the arrow of time. If the equations of motion were not tau symmetric, that asymmetry would be shown by the motion of antimatter. Since negative and positive tau are identical in this regard, we have wrongly assumed that negative tau simply does not exist. But the equations of motion do not have an arrow of time. Tau can go in either direction. And there is nothing to indicate that time, on the other hand, has any such orientation at all. Forward and backward apply to axes, but the mathematics that imply that time has this kind of dimensionality apply to tau, not time. Asking why time always goes forward is a bit like asking why life forms grow. Time has no direction. Like tau, there is no arrow of time. Quantum theory makes very accurate predictions about the behavior of subatomic particles, and much of classical physics emerges when the theory is taken to the classical scale. It is widely regarded as our most successful theory, but at the center of it lies the measurement problem. An obvious contradiction exists within its foundational axioms, and this contradiction is the principal reason why quantum theory, despite its success, remains a controversial subject. The Dirac von Neumann axioms are a set of rules for practicing quantum mechanics. The first group of rules describe a so-called wave function as it evolves in time. This picture is purely deterministic. If you are given a complete description of a system at any point in time, you can use the math to predict how it will evolve with 100% accuracy. The second group of rules are referred to as the measurement axioms, as they describe what happens when the physicist takes a measurement. The first set of equations may be purely deterministic, but the measurement axioms introduce probability. These two groups of rules represent two different descriptions of the underlying physics, but no proper guidance is given to help the physicist determine when each set of rules apply, beyond the statement that the measurement axioms apply when the physicist measures the system. This ambiguity is what inspired Erwin Schrödinger's famous cat thought experiment. According to the initial axioms, a quantum system exists in a state of superposition, that is to say, all possible outcomes exist simultaneously. So Schrödinger imagined a box. Inside the box is a cat and a device which releases a poison when a radioactive isotope decays. The initial axioms state that the isotope, until measured, has both decayed and has yet to decay. The measurement axioms state that a definite outcome only occurs when the isotope is measured. Since the isotope has both decayed and not decayed, the poison has been both released and not released, and therefore the cat is both dead and alive. That is, until the physicist opens the box, thus measuring the system and forcing it to collapse to a single outcome. Schrödinger's purpose behind creating this thought experiment was to highlight how ridiculous these rules are. Two sets of rules, separated by a word, which is not explained. This ambiguity is why quantum mechanics has taken on an almost spiritual meaning for some, since the rules seem to suggest that simply by measuring things, human beings are able to alter the universe. While the quantum mysticism that has grown out of the measurement problem has no basis in science, experiments do prove that a physicist, by measuring a system, changes the outcome, and in ways that are hard to explain with our current understanding of coordinate time. The probabilities that arise do not exist at a singular point in time. They are spread out across time, challenging our understanding of causality, and these observations have led to some extreme-sounding hypotheses. The many-worlds interpretation states that superposition is physically real, and that every outcome does in fact occur. And reality itself branches into a complicated network of universes, each with a definite outcome. Superdeterminism states that the entire universe is a single, unchanging, four-dimensional block, and we are simply riding through it with no hope of changing the outcome. There are retrocausal interpretations, which state that the future can affect the past. And there are some more sensible-sounding theories, but none have been able to properly explain the observations. The most famous and popular, however, is the Copenhagen interpretation, which adds very little. Copenhagen simply restates the axioms in plainer language, while adding a positivist viewpoint, claiming that only the measured outcome is physically real. Broadly, the gap between the two groups of rules became known as the Heisenberg cut, and in some ways it represents the separation of classical and quantum mechanics. Equivalent time theory offers a simple solution. The fourth dimension is not time, it is a clock, a physical dimension which has a symmetric relationship with the flow of time. By treating it as a physical dimension, recognizing its periodic motion, and by being consistent with the existing mathematics, a possible solution to the measurement problem immediately appears. There is a logical progression from Newton to Einstein to Dirac. Isaac Newton understood the work of Galileo and the relativity theory that he created, but realized that for physics to work, it had to be based on some invariant quantities. Newton postulated two: time and space. 1 second is the same for everyone. 1 meter is the same for everyone. However, our study of electromagnetism could not be resolved with that view. Einstein realized that there was only one invariant. He took the invariant time interval and invariant space interval and merged them into a single space-time interval. Time and space are now conjugate variables, but the way to interpret this new interval is not entirely clear. The way that I interpret it is that time, tau, is the analytic continuation of a fourth physical dimension. All objects move at the speed of light, and that a stationary object is simply pointing in the tau direction. Acceleration is the change in angle between space and tau. This concept can be easily expanded on to include lessons from quantum mechanics. The Planck relation can be rewritten to represent an invariant interval. Now, energy and wavelength are conjugate variables, with this representing a kind of length contraction equation. As the energy of light increases, its wavelength contracts. However, this equation is not detailed enough to describe matter. For that, we need the Dirac equation. This describes matter as being constrained by mass, phase, and momentum, and solutions to it include a Lorentz scalar with 2 conjugate variables. By reparameterizing it, a complete record of the particle's path along this new, improved interval can be represented mathematically. And now I state the one and only postulate of my theory. The angle associated with tau, which is a physical coordinate, must match in order for an interaction to occur. Essentially, I am enforcing a form of locality. This results in 2 mutually exclusive interaction types, continuous and discontinuous, entanglement, and what I have called periodic synchronization events. Imagine 2 clocks existing in the same space. They are synchronized, so the hands of each clock are in continuous contact. This is entanglement. Now imagine 2 clocks that are running at different speeds. The faster clock will eventually catch up to the slower clock, and for an instantaneous moment, they will show the same time. At that moment, the measurement axioms apply. The synchronicity constraint, or Dirac's sigma, shows that when 2 particles are perfectly synchronized, they will remain that way across any distance in space as long as their momentum is not disturbed. Einstein's relativity fundamentally breaks when events can affect each other while being separated in space. But this equation not only shows that entanglement can exist over any distance, but expressly forbids the transfer of momentum, something which can only occur locally, as it breaks the constraint. Only periodic synchronization events can transfer momentum. The Born rule differentiates between the phase evolution and the phase overlap with the measurement devices or other interacting systems. This makes equivalent time theory a hidden variable theory, as the probabilities represent our inability to predict the progress of a particle's phase prior to measurement. Classical measurements require an exchange of momentum, as the measurement device must be moved. This means that classical measurements are always periodic synchronization events, and as such require the measurement axioms. But a physicist measuring the system is not the only thing that leads to this outcome, and indeed at the classical scale, periodic synchronization events will be common. The particles that make up most objects are moving in a chaotic fashion, and will have different values of sigma. So, a classically sized object like a cat will certainly not be in a state of superposition. Modern physics has tried to maintain a culture of pure operationalism, focusing heavily on the mathematics. I believe that this is because both of the dominant theories that we use, general relativity and quantum theory, are incomplete, and that incompleteness is not in the peripheries of these theories, but at their core. The measurement problem is built into the fundamentals of the theory. Einstein's relativity, on the other hand, describes space-time in a way that is not compatible with our everyday observations, and this contradiction is not properly explored. These issues are often described as philosophical, despite the fact that they relate to empirical observations, and this seems to me like a convenient way of dismissing valid criticism, rather than admitting that the physics is simply incomplete. Although equivalent time theory is consistent with the existing mathematics, what I find most compelling is how much it looks like the world as it is presented to me. There is no invisible, intangible time dimension, no hyperbolic geometry, no cats that are both alive and dead. The universe is classically three-dimensional, and time manifests simply as change. This matches my everyday experiences, unlike the ontologies, which underpin most interpretations of relativistic quantum mechanics. Thank you.